Hey everybody. Last DL, we started talking about heat capacity as it relates to the number of modes that particles in a substance have. We saw that for solids and liquids, the number of modes per particle was generally 6, and the heat capacity was determined by this amount. But for gases, we found that the heat capacity can vary depending on what kind of particle we're talking about. For more complicated molecules with more modes, the heat capacity will be greater, while for simpler molecules or individual atoms with less modes, the heat capacity will be less. But there's more to the story than this. When we add heat to a gas, it's not just its temperature that changes. Other properties of the gas change as well. So when we're thinking about heat capacity, we need to consider these properties too. In this DL, we're going to talk about heat capacity at constant volume. So what does this mean? Let's suppose that we put a bunch of gas in a box. The box is a fixed size. It can't get bigger or smaller. Heat capacity at constant volume just means we're trying to figure out how much energy we have to add to the gas in the box in order to raise its temperature while its volume is remaining fixed. Next DL, we're going to switch it around and look at heat capacity at constant pressure, where the volume of the gas is allowed to change, but the pressure is allowed to stay the same. To do this for constant volume, we're going to use another simulation. In this simulation, we're going to add energy to a gas that is going to be fixed at a constant volume. And we're going to see how that addition of energy affects the temperature. As before, I'm going to turn my camera onto the simulation so that you can read the values yourself. Once we've collected the data, you're then going to graph it in order to determine the heat capacity. Keep in mind, the heat capacity is equal to the energy added to a system divided by its change in temperature. If we want to make a graph that will allow us to find heat capacity, we need to record those two things, the internal energy of the gas as well as the temperature. However, because we're thinking about heat capacity at constant volume, as compared to heat capacity and constant pressure, we want you to also collect the volume and the pressure of the gas at the various stages. Remember that the volume should always be the same, but the pressure is going to vary. All right, here's our simulation for heat capacity at constant volume. The size of the container will remain the same for this entire simulation. In this simulation, there are 100 particles of gas. Write that number down somewhere because you're going to need it later. We're going to add energy to the system in steps and see how that affects the values of some numbers. As before, the numbers are up here on the top right-hand side. There are 4 numbers that you need to be measuring at each step. You need to be measuring the total energy of the system, the temperature of the system, the pressure of the system, and the volume of the system. Start out by writing down what the values are right now, and then we'll add energy to get new values. We're going to add energy just like we did in previous simulations. We're going to add 5 times 10 to the negative 20 joules of energy. Ready? Let's add another 5 times 10 to the negative 20 joules. We'll add another 5. We'll add another 5. And now we'll add our last bit of energy. If you need to rewind the video or pause it in order to take the data, don't hesitate to do that. Let's just think about this qualitatively for a moment. What do we expect to happen to the particles in the gas as we add energy? Well, we should expect that they should speed up. Even if these particles have more than one atom, we expect that some of the energy that we add to them should go into their kinetic energy, which means that they should be speeding up. If you go back to the beginning of this video, you should be able to see the difference between the particles at the beginning without any heat added and the particles at the end with all the heat added.